Alright, so welcome back, and now we're moving right along into static and current electricity. Static electricity is an imbalance of electric charges within or on the surface of a material. The charge remains until it is able to move away by means of an electric current or electrical discharge. Matter is composed of atoms. Atoms are composed of three types of particles. We have protons, which are positive particles, neutrons, which are neutral particles, and electrons, which are negative particles. An atom has no charge because they have the same number of positive as well as negative particles, giving it a total charge of 0. Most materials are neutral. Rubbing materials together can cause friction. This causes the movement of electrons from one material to the other. The only particle that moves from material to material is the electron. Why does the proton or the neutron move? Why doesn't the proton or the neutron move? Right, if you look at this picture, you realize that the protons and the neutrons are trapped into something called the nucleus. So those particles are encased, right? And then you have the electrons, which are free to roam and move about. So the transfer of electrons results in both of the materials becoming electrically charged. When extra electrons enter an object, the object becomes negatively charged. When electrons leave an object, the object becomes positively charged. Rubbing a polythene rod with a dry cloth will cause electrons to move from the cloth to the polythene rod. As you can see in the picture, you have them with same amount of charges making them neutral objects, and with a good old rub you have the movement of electrons from the cloth moving into the polythene rod. We have more electrons than protons, so in that sense the object now becomes negatively charged. Now the opposite will happen with a perspex rod, is when it is rubbed with a dry cloth, and it says explain what will happen using a drawing. So let's start with a drawing. We're going to try to fit it in somewhere. Belt tip. So I'm going to draw the cloth. I have the cloth, and I'm going to put plus, plus, minus, minus, plus, plus, some more minuses, right? And then I'm going to have the perspex rod. So I have plus, and we have a minus here already, minus, plus, minus, plus, 3, 3, and then we have, so I'll just leave it like that. And then when it's rubbed, we know the perspex is going to become more positive, so therefore the electron is going to leave the perspex rod and enter the cloth. So the cloth is going to become more negative. So, and the positive charge is steady, they don't move. So we're going to have plus, 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 1, 2, 3, 4, plus, and then the negatives, I'm going to put them in there, 1, 2, 3, and then I'm going to just leave this wholly positive. You don't have to leave it wholly positive, you could have more, but because of the space, I just left it like that. So opposite charges attract, like charges repel. Okay, so if you have two positive objects, they're going to repel. Two negative objects, they're going to repel. If they're neutral, there'll be no attraction or no repulsion. But if you have one that's positively charged and one that's negatively charged, they will attract each other. Okay? So those are the laws of attraction and repulsion. Induced charge. So a neutral object can become charged when a charged object is placed next to it. This process is referred to as charging by induction. So here we have a metal sphere which is neutral, and then we put something that is entirely negatively charged next to it, causing a separation of charge, right? Temporary charging by induction. And so we have the positive charges being attracted and basically the negative charges repelling. Now what happens is that the negative charges are removed by placing some sort of wire into the ground, and so they all travel towards the ground, and now the object is now positively charged. So that is called charging by induction. What would happen if a perspex rod was placed next to the sphere? Well, the perspex rod would be positively charged, so we would have all the negative charges being attracted to it, and then the positive charges would just repel, right? And then you could, I think that it would more likely turn to be positive still, because then if you want the charge, then what would happen is that all the negative charges would actually leave and enter the perspex rod. They would have somewhere to go, leaving this sphere positive, right? So let me see if I could draw the idea for you. So if it was a perspex rod, it would be positive, all these positive charges. Then you have this sphere right here. Then you're going to have all the negative charges being attracted, so you're going to have them being attracted. And eventually, because electrons leave, they're going to enter the perspex rod, and then you're going to still end up with a positively charged sphere. If you have a different idea, let me know. Now, useful applications of static charge. Lightning conductors. So, tall buildings are often fitted with a thick copper strip running along its length to protect the building from lightning strikes. So here we have a cloud suffering from or experiencing a bout of separation of charge. And so the thundercloud is charged, right? And so the ionized air ionized with a high concentration of charge at spikes, and we have some positive charge being attracted to the spikes. And what's going to happen, they're going to have all the negative charges being attracted to these positive spikes, and because they're so pointy, it's easy access, really easy access. And so these electrons enter these points, these charged points, and they go right down the copper metal into the ground, where there's also a separation of charge due to the presence of these charged clouds. And so the negative charges are attracted to the positive ones, thereby making the cloud less violent, right? Making it become mostly positive. So another useful application of static charge, electrostatic spraying. When vehicles are spray painted, electrostatic charging is taken advantage of. The paint passes through the nozzle and becomes positively charged due to friction. The body of the car may become negatively charged via induction due to the positive particles or by being connected to a negative terminal. This attracts the positively charged paint particles. Okay, so that's how you see that. It's negatively charged, the body of the car, and the paint droplets are positive, so that's why you have a nice smooth paint job on your car. Photocopier, they also use static electricity or static charge to their advantage. You have the drum, and a shadow image of the printed item to be copied is cast by a beam of light onto a positively charged plate or drum. The charge leaks from the plate where light is reflected to it from the white parts to the paper, leaving a positively charged image on the drum. Then the negatively charged toner is attracted to the positive image, and then the drum rotates and presses onto a sheet of paper. Heat and pressure are then applied to fuse the toner firmly to the surface. Then we have hazards now. So whereas we had the useful applications of static charge, we're going to look at the hazards of static charge. Now, lightning. A cloud becomes charged due to friction between layers of air and water molecules rising and falling within it. The base of the cloud usually becomes negatively charged, while the top of the cloud becomes positively charged. And that's simply because the earth is positively charged. So that is why you have this separation, this negativity here, and the separation is because the earth is positively charged. And because of that, because of this presence of negativity, we also have separation of charge in the earth. So up here will be positively charged and down here will be negatively charged, right? So it's like a ripple effect. And so sparks occur between opposite charges in the cloud. The negative charge on the base of the cloud repels electrons further into the ground below. When the potential difference between the earth and the cloud gets large enough, electrons and negatively charged ions rush from the cloud to the ground. The high-speed particles crash into air molecules, knocking electrons out of them and creating pairs of oppositely charged ions. This produces lightning, which gives off heat and eventually sound, which is known as thunder, due to a rapid air expansion and increase in air pressure, which produces a shock wave. Charges from fabric in the seats of a vehicle. That's another hazard. This usually happens in dry regions or if the air in the car is very dry. The person can become charged by friction, and this becomes a hazard if they are going to use the metal hose or the gasoline pump, which can cause a flash fire. It is best to discharge oneself by touching the metal body of the car. I don't know, me as a driver, I've experienced this when the AC is running and the air is very dry in the car. I'll be holding my rubbing is from letting the wheel drag between my hands, and it's covered with a piece of fabric. So sometimes when I come out and I touch the car, I'll get a zap. I'll be like, zzz. So it is true. The fabrics and everything in the car can cause static. Now, refueling of vehicles. Large electrical charges can build up on vehicles when they move due to air resistance or other frictional forces which cause the transfer of electrons. Car tires can build up lots of friction which can cause explosions during refueling. Modern cars are now fitted with special tires to avoid the buildup of too much friction. The refueling of aircrafts due to the movement of fuel can cause a buildup of charge which could lead to an explosion. This is overcome by connecting the tank and the person who is refueling the tank to a conducting cable to allow the charge to dissipate safely. Mills. In grain or flour mills, where there's a lot of dry air and or powder in the air, sparks can cause explosions. In electronics now, microprocessors and other integrated circuits can also be destroyed by static electric fields. Alright. An electric field is a region of space in which a charged object will experience a force. Okay? Now, the picture above shows the direction of electric fields near a positive point charge and a negative point charge. Field lines may be used to represent the strength and direction of electric or magnetic fields. So we have it here as going from positive to negative. Remember that? When it comes to electricity, it's going from positive to negative. Important properties of field lines are: the lines never touch. 2. There is a longitudinal tension within a line. 3. There is a lateral repulsion between lines that are close to each other. Field lines at the top and bottom of the plate bulge because of lateral repulsion. These are not uniform. 4. The field is uniform where the lines are evenly spaced and parallel. You can see it here. So they're very straight in between here. As you reach the end, they're not equally spaced, and so they start to bulge. Electric field lines are directed from positive charge to negative charge, so you need to remember that. So here we have the interaction, the field lines and the interaction between like charges, and we have all the lines going towards the negative, because that's how they're supposed to be, so they're going towards the negative. And they're not attracted to each other. If it's opposite charges, then you will have positive going towards the negative. Okay? And then you have now a plate, and you will see positive going towards the negative. Okay? Van de Graaff Generator. Rubbing a rod with a cloth can only separate a small amount of charge. A Van de Graaff generator can be used to investigate the effects of electric charge. To produce a larger buildup of charge, a Van de Graaff generator can be used. If you touch the VDG generator, all the electricity will pass through your body, giving you a big shock. It can actually be dangerous. You can be protected from the ground by standing on a piece of rubber or plastic. We said plastic and rubber are insulators since charges can travel through them very easily. When you touch the generator now, the charges can't get to the ground. You are now filled up with electrons. The electrons don't like each other and are trying to get as far away from each other as possible. Usually, this makes your hair stand up because it is filled with electrons, which are repelling each other. Below are links to videos illustrating how the Van de Graaff generator works. When you have time, you can look at these links. And here ends our part 1 of static and current electricity, magnetism, and transformers. See you around for part 2.